In the forward direction, however it's shown, we're trying to show that. So, by the way, do you all recognize what is this? I'm not asking for the name. Geminal diode. What are geminal diodes?
To
Hydrate. It's a hydrate. Does everybody recognize that? It's a hydrate. Do you all recognize, therefore, where was the, okay. Can you tell me, if I were to, what will I get? Ketone. That was my question I was trying to ask. Do you all recognize how this hydrate is from a ketone?
yes. Yep.
Everybody good? Can you tell me what that ketone will be? Where is the ketone carbon? Where is the carbonyl carbon?
Right in that CV, the gym.
It's that one. Exactly. Because it is the carbonyl carbon, the C double bond O carbon, which is going to be the hydrate carbon. That's where the reaction's happening. So can you please tell me what is the product? When a hydrate is being hydrolyzed, what is it going to create in this case?
CO instead of
CO instead of the?
Gemini.
Do you all agree? Please take a couple of minutes, write a mechanism to show this reaction. How is this happening? Let's follow the logical steps, the patterns, so on and so forth. If I took a certain route this morning to come from my home to work, how am I going to go back?
Same way.
But just the opposite direction. So you got to think about forward, which means what should be the reverse steps to go in the reverse direction. Anybody? Oh, take a couple of minutes. Okay, sorry, forgot about that. Suggestions. First step.
One of the
Louder.
water takes a proton.
Water cannot take. There's no water here.
The OH.
I mean, sorry, there is water. Sorry, I said that totally wrong. But it's already taken the proton, right? That's why you have H3O plus, because water already took a proton, the acid. That's why we have that.
One of the OHs takes a proton from that thiolic acid.
So notice maybe I shouldn't have erased that. Shoot, I erased that. When we were writing the mechanism earlier for, what was it? Benzaldehyde? Was it benzaldehyde?
Yeah, benzaldehyde.
What was we wrote the first step where this gets protonated, right? Am I right?
Yep.
And then the nucleophile attacks and becomes, and then what? What happens next?
No, we do take a
This oh no, you're telling me there. Yeah, hold on. I'm just writing this again so we can compare.
OH.
What happens next here?
OH2 donates a proton.
OH2 donates a proton, so this guy loses a proton and you get the hydrate. Did that make sense?
Yes.
Now we are going opposite direction. So whatever was the last step is going to be the first step. So what's the last step here? Giving a proton. What's the opposite of giving a proton?
Accepting
Taking
a proton.
Exactly. Where is that proton coming from?
Hydronium.
Hydronium. Which one?
Either.
Doesn't matter. Exactly. So one of the OHs gets protonated. Do you all see that? It's the exact opposite of the forward. That was the last step here, so we are going this way. So what's going to be the next step? Going this way. Here water was added, so what's going to be the opposite of water?
Water was taken out.
So that's a good leading group. Just the opposite. Make sense, everybody? So what does that create? When water is kicked out, what does that create?
Cation.
Good. And what's so special about this cation? Because you've seen it before.
Resonance.
It's a tissue.
Very stable, resonance stable. It's tertiary, sure, but more importantly, it's resonance stabilized. Resonance stabilized coming from where? Where's the resonance stabilization coming from?
Oh, wait. Oxygen.
What's the resonance structure look like? Agreed? Where are we?
Right there.
Okay.
So what should be our last step?
Oxygen.
Say that again?
Water takes a proton.
Because we started with that. Exactly. Water is going to come in, take this proton, give us the proton. Notice how both of these mechanisms are direct opposite each other. It depends on what is it we are trying to explain. Are we trying to explain the formation of the hydrate, or are we trying to explain the hydrolysis of the hydrate to give the ketone or the aldehyde? But does everybody understand that?
Yes.
Everybody okay? Questions? Okay, now hydrate formation for us organic chemists is like, okay, so what? What are you going to do with it? It's not so useful. It's more of a use to biochemist. What is more useful for us organic chemists is something similar to this called acetal formation. Is that number 3? Reaction
Yeah.
number 3? This is very useful for us. Now, please again, look at patterns. I'm a huge proponent of patterns because patterns help us make predictions. We just saw that an aldehyde or a ketone, acetal, Al, aldehyde or a ketone can react with water. I'm going to write water this way, in presence of an acid. We just saw this. Can someone tell me what's the outcome? What does it create? Sorry?
Geminal diol.
Sorry?
Geminal diol.
Diol, aka?
Hydrate.
Do you all agree?
Yep.
We just saw this. Okay. So, if instead of water, I had an alcohol, right? What change would you make there?
Oh, well, it's a ketone instead.
Don't, again,
No,
I
no, no,
feel
never
like
mind.
you guys are
You have an
overthinking it.
ether and a
Yeah.
hydroxyl.
One of these is,
It's an R.
that's it.
Yeah.
It would be an ether.
Although that's not it's not an ether because there's that geminal OH there, so we can't call it an ether. This is called a hemiacetal. Hemi means semi. It's halfway there. Let's just focus on this step. We'll take it to the acetal part of it later, but let's just focus on this step. You know what, let me just write it here. So if, as an example, just an example, let's say we have cyclohexanone ketone, and I am reacting it with ethanol in presence of an acid catalyst. Can you take a guess what the product would be? Just that step. What would the product be?
An alcohol. What the
Got it.
COO is an alcohol and an ether.
Which one?
Ethyl.
OET.
OET. Yeah.
Right, ethyl. Agreed. Agreed, everybody?
Yes.
We have basically added this across the pi bond with OET going here and H going there. H goes to the oxygen, nucleophile goes to the carbon. Everybody okay? Cool. Now that's just a hemiacetal though. Hemiacetals are not very stable. This step is an equilibrium step which is mostly in the direction of the keto form. So we don't isolate the hemiacetal. Yes, it's created, we write a mechanism, but we can't really do it well because the equilibrium actually favors the opposite direction. What we do instead is take it one step forward. This is not an equilibrium step. Second one is predominantly in that direction and reacted with another equivalent of alcohol. So two equivalents of alcohol if you see. Any guesses what the product might be? If you were to take a random guess. Okay, maybe not that random, but yeah.
The OR groups are the same.
Okay, yeah, what would the product be though? What is that? What are you trying to say, Carter? What would the product be?
2 ORs.
2 ORs.
And the OH.
But OH, how can carbon have 5 bonds?
Oh.
Carbon cannot have 5 bonds. Anybody?
What they
Carter was right that the OH gets replaced by OR. That is called an acetal. Acetals are all around us in your biochemical systems. Acetals are all around us. Sugars mostly exist as acetals in the natural conditions. And that is extremely useful to us synthetic chemists. This is very, very useful to us. But anyways, coming back though. So if I were to take this example from this hemiacetal, which is not isolated, if I were to react it with another equivalent of ethanol, what would the product be? Anybody?
Diethoxycyclohexane.
Good, that's a great way of naming it, but then you would have to call it 1,1-diethoxy, right? Because it's on the same carbon. So we will get this acetal. This is an acetal. Are you all good, everybody? Make sense so far? Let's write a mechanism for this entire process, starting from cyclohexanone all the way to the acetal. Again, please focus on the patterns. Please focus on the patterns. Can someone tell me what's going to be the first step? So we're starting with cyclohexanone. What's going to be the first step?
The oxygen's gonna take a
Because there's an acid. If there's an acid, you got to protonate. Period. If there's an acid in the system, you got to protonate the oxygen. Without thinking, you got to protonate the oxygen. Agreed?
Yes.
Okay. Next step. Once the oxygen is protonated, what is going to happen next?
Then the ROH is gonna attack
The nucleophile, which is the alcohol in this case. What is the alcohol in this case?
Ethanol.
Will attack. Guys, there's no difference in this mechanism and the hydrate. The only thing is, instead of H2O, we have the alcohol. Otherwise, it's exactly the same. Agreed?
Mm-hmm.
What will that create? What will this need to do?
Give away a proton.
Have you so far seen anything different? So far.
Was it R2?
That's the only difference, right? As far as the mechanism is concerned, there is zero difference so far. Do you all agree? We get the hemiacetal. Now, Hemiacetals, as I said, are not very stable, so we don't really work with this unless there was a reason to stabilize this. We generally go all the way to the acetal. Is everybody okay till there? Okay, now let's process the second step. What do you think will be the first step for the mechanism of step number 2? For here, let's just call it 2 and 1. What do you think will happen first? Go with your gut. Protonate the OH. There is acid. You can protonate one of the oxygens, right? Protonating which oxygen helps us go forward? Because if you protonated this, wouldn't we just go back?
In the OH.
Oh.
Right? So protonating the OH helps us go forward, exactly. Everybody okay?
Yep.
When you protonate that, what does OH become?
A good leaving group.
Do you all see that?
Yes.
Please tell me that, what was I going to say? I was going to say something, shoot, the words have gone. I'll come back. Everybody okay?
Yes.
What is that going to do? What does your gut say?
Create water.
Create water by kicking this out.
Yes.
What's left behind? Anybody?
A carbocation.
Have you seen this before?
Yes.
What's so special about this carbocation?
It's on,
Again,
Resonance stabilized.
Exactly. Same thing. No difference. The only difference is instead of H you have ET. Big deal. Agreed? Yes? Oh, where are we going? Hold on. Hold on. Okay, fine. Sorry, I totally lost track of where we were going. But it's okay, we are okay. But do you all understand the resonance stabilization part of this carbocation? Okay, cool. What do you think will be the next step though?
Another ethanol toxic.
Exactly. That's why we need two equivalents of the alcohol, one to get us to the hemiacetal, the other to take us to the acetal. So the second one comes, where will it attack? Now again, here is a choice, guys. Again, some people write it this way, some people write it that way. It doesn't really matter because it means the same thing. You might choose to just do it there. Fine, totally okay. Or you might decide to put it here and then doesn't really matter because those are resonance structures. Neither of them actually exist. What exists is the hybrid. So it doesn't really matter. Do you agree that either way you show it, you will end up with this guy? Agreed? So what do you think needs to happen next?
Oxygen gives away a proton.
And we are going to show it this way because we started with H plus, we are going to create an H plus. And that gives you the acetal. Make sense? Everybody okay? Now, is this okay to do? I know I have too many things over there, so if I may erase these arrows, curved arrows, so not have too much crowd. If I were to do this, what would you say? If you were the grading person and the student does this, what would you say?
No.
Please don't do that. Carbocation has to be shown. We know it's created, so you got to show it. Mechanism is not about writing shortcut answers. You got to show every step possible that that takes you from the reactant to the product. We can't skip steps.
There's no shortcuts.
Is that okay, everybody? Yes?
Yep.
Let's do it again. This is one of those mechanisms that's extremely important. It comes up all the time. So let's write it again. I just did that.
Acetal mechanism.
Say again?
Is the acetal mechanism?
Acetal, yeah, exactly. Okay, let's do another one, but this time. aldehyde. Are you guys familiar with this guy, TSOH?
Yes.
Tossic
What is-
acid.
Toxic acid, exactly. It's a very strong acid, guys. So if you see TSOH, please remember it's an acid. It's a strong acid. Okay, show me the product all the way. We are going all, sorry, my mistake. 2. So what will be the product and then mechanism? Feel free to come to the board and write your answers.
I know the product.
Mm-hmm.
I'll write that down.
Mechanism, anybody?
We're trying.
Because there's an acid, protonate first, then nucleophile, then lose a proton, then protonate, pick out the leaving group, and then the nucleophile attacks carbocation product.
Simple.
So it's that logical sequence of events. Do you guys remember the day in 261 when we started learning curved arrows?
Yeah.
And now you guys just go flying here and there. Isn't that cool? No. The reason, one of the reasons I love third quarter is also to see how from first quarter, some of this stuff is like, oh yeah, of course I know what you're talking about.
Yeah.
Yeah,
At first
exactly.
it was like, it was like, what?
Curved arrows.
I still remember that day when we introduced curved arrows and it's like, what? What's going on here? And it's like, yeah, that's called learning.
OH. Okay.
Cool.
Okay.
You're missing
I'm
something.
missing something. Is-
Those electrons went to oxygen, right?
So would that come down?
So you can, if that's how you, that's another way of drawing it.
Or do I just need to do that?
Either. So see,
Okay, either works.
whether you draw the resonance structure or this one doesn't matter.
Okay.
Means the same thing.
Okay.
Mhm.
Spot this in the arrow.
Mhm.
Yes, you have a question?
Yeah.
Yeah.
Took a proton was lost.
Where did it, yeah, it just lost in there to make this
Yeah,
neutral.
Exactly. Do you all agree? Everybody okay?
Just look at something forever.
Yeah? Cool. So that's making an acetal. Generally speaking though, if you're going to talk to an organic chemist, they will not work with those kind of acetals. We like to use cyclic acetals. Because cyclic acetals are more stable than the ones we've seen so far that are not cyclic acetals. Cyclic acetals, where the acetal is either a 5 or a 6-membered ring, are more stable than acyclic acetals or acetals that are not cyclic. So far the couple of examples we've seen, they've been acyclic acetals, right? I mean, this part is not a ring structure. But cyclic acetals is actually better. And especially cyclic acetals that are a 5 or a 6-membered ring. So, for example, what would I get? Take a guess what the product would be, please. Instead of taking 2 alcohols, we are taking 1 alcohol, but it's a diol. Everything else is exactly the same. What would the outcome be? Uh-huh.
It's like cyclopentane.
But it's an acetal. So, this carbon, where are my colors? Okay, well, let me call it 1, right? Because that's where the reaction is going to happen. Will the oxygens be part of the acetal? Are these oxygens part of the acetal?
Yes.
So 2, 3, 4, you get a new 5-membered ring. What would that look like? That's the same. That's my carbon 1, which is the acetal, so it has to be connected to 2 oxygens, right? Agreed? And what are these 2 oxygens connected to?
2 carbons.
2 CH2s. It's a 5-membered acetal. Let's write a mechanism. Again, it's that muscle memory, guys. The more times you write the mechanisms, the easier you'll remember it. So what's the first step? No difference. No difference
The
here.
oxygen is protonated.
Oxygen gets protonated. Okay. What happens next? Oxygen got protonated. What is it waiting for? Nucleophile.
A nucleophile.
What's the nucleophile?
Our diol.
It's the diol, of course, one of the alcohol groups from the diol, one at a time. Oops, sorry, wrong. Will attack the electrophilic carbon, right? What will that create? OH and O12 OH. And what is this guy going to do?
Get in.
What is this guy going to do before getting in? There's no leaving group yet. What is this guy needing to do?
Donate.
Same mechanism, guys. There's no difference. What is this supposed to do now?
Donate a proton.
Deprotonate. Because there's an extra proton there. It will give away a proton. What will this intermediate do? Louder? We need a leaving group. We don't have a leaving group yet.
So the OH is going to get
Protonated, exactly. The H plus will protonate the OH. No difference, exactly the same sequence of events. Will get protonated, okay, so that becomes a good leaving group. And 1, 2, 3. Agreed? What is this guy going to do?
The leaving group leaves.
And creates a
Creates.
stable carbocation. Is that right?
Yep.
Is there any difference? What is this guy going to do? What happened after you got the carbocation?
The resonance stabilized.
Fine, but the nucleophile attacks.
Again.
Intermolecular.
Exactly. The only thing is that second nucleophilic attack is intramolecular, not inter. So the intramolecularly it attacks. There's no difference otherwise. What does that end up creating? Creates a
ring.
5-membered ring. What is this going to do?
Deprotonate.
Deprotonate gives you the product. Same mechanism. Make sense, everybody? Yes?
Mm-hmm.
Cool. Please tell me. So in synthesis, in organic synthesis, I know some of you are doing these research projects for your bio, and maybe you've come across acetals like that. We, in organic syntheses, if we need an acetal, and we'll talk about why do we need an acetal, but we generally go for either a 5-membered acetal ring or a 6-membered acetal ring, because they are definitely more stable than the others. So can you please tell me, just the products, only the products, not asking for the mechanism, just the products. Of course, I would encourage everybody to practice mechanisms. Write them over and over and over again. Now this one is really interesting. I don't want you guys to get bored of seeing toxic acid and think that's the only thing possible. Any acid. Maybe this mechanism we should write. But please, I just need products for now. Mechanisms are homework.
You want us to write them?
Yeah, please, absolutely, yeah. Oh, you lost a carbon. Yeah. Oh. Got it. Exactly. This is going to be a 6-membered ring because 5 atoms are coming from here, 1 is coming from here. Yeah. What about this next one? It's a very interesting one.
Can I try?
Yeah, please.
Yeah.
No, try and give it your shot. And maybe sometimes numbering the atoms helps keep track of what size and where, if that's something you want to do. You're going in the right direction, Camilla. Complete it. Okay. Perfect. Perfect. It's an acetal. If you think about it, it's an acetal because it's a geminal diether. Geminal diethers are acetals. Do you guys agree with these answers? Do you want to write this mechanism or you got it and you'll do it at home?
I'd like to try that mechanism here.
Try. Go ahead. Try it out. First step. Where's my pen? First step.
Protonate the
Which oxygen? There are 3
the
oxygens.
double bonded
Makes
oxygen.
most sense to protonate this time. Okay, if you protonate this one, what's next? Go on.
Oh, the nucleophile next.
Good. Where is the nucleophile?
Either one of the OHs on.
Exactly. It's exactly the same mechanisms except both nucleophiles is intramolecular. Making a 5 or a 6-membered ring. That's the important part. So what size ring would this create? 1, 2, 3, 4, 5. Isn't that right?
Mm-hmm.
Agreed?
Mm-hmm.
Okay, so what's next step? Next step? Oh, wait, I forgot something. There we go. Next step?
One of the OH. No, the middle
No,
one.
you got to deprotonate first.
Oh.
Got to deprotonate this, right? And when you can I just skip that? Because you can draw this. Everybody okay?
Mhm.
And then what?
And then the middle OH group,
Uh-huh.
gets protonated
Gets protonated.
and then becomes a good leading group.
Exactly. Exact same steps, guys. No difference, except both are intramolecular. Yes, can complete the rest. Make sense? Questions? Okay. So, as an organic chemist, I prefer cyclic acetals. And why is it that I prefer that we use acetals? What's the purpose of acetals? So if we have an acetal, guys, an acetal, just as an example, this is an acetal, right? Because it's a diether. Acetals, shoot, sorry, could I do this again, please? Sorry.
Yes, go ahead.
I'm so sorry. I'm so sorry. So if you have a ketone, I can convert that into an acetal. In order to make this acetal, I need to use a diol with an acid. Isn't that right? Of course, it's an equilibrium reaction. Equilibrium favors the acetal. For cyclic ones, equilibrium favors the acetal, blah, blah, blah. But this can go back into the ketone very easily. It's very easy to hydrolyze the acetal back into a ketone. Can someone tell me what would I need to use? Okay, maybe you can tell me what to use if instead of putting the alcohol there, if I wrote the alcohol here. These two with an acid produce an acetal, but the acetal can go back into these two. What do I need to use?
A base.
No. Let's talk about the catalyst later. What's the reactant? What's the difference between, you might want to count your carbons and hydrogens and oxygens. What is the difference between the acetal atoms and these atoms? How many carbons there? Come on guys, we can do this fast. How many
1,
carbons
2,
there?
2 extra.
3, 4, 5, 6, 7, 8.
Total, in here, total number of carbons.
8 carbons.
8 carbons, do you all agree? Is that what you meant by 2 extra? Okay. 8 carbons. How many total carbons here?
8 carbons.
So carbons is the same. Agreed?
Mm-hmm.
How about total hydrogens here?
2, 4, 6, 8, 10, 12, 14.
Do you all agree?
Yes.
14 hydrogens.
How many total hydrogens here?
14.
Careful, slow down, count.
Oh.
Don't be in a rush.
2, 4, 6, 8, 10, 12, 14.
How many? Total how many?
16, yeah.
Why so long? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
16.
Isn't that right?
Mm-hmm.
What was there? How about
H14.
oxygens? How many total oxygens
2.
here? Total oxygens here.
2.
2.
How many total oxygens there?
3.
What's the difference?
Oxygen.
No,
And
please.
ice.
What's the difference between the two? Water. Water. 2
Two
H's
H,
and 1
one
oxygen, that's water. It's a hydrolysis reaction. All we are doing is adding water.
Mm-hmm.
Do you all see that?
Mm-hmm.
Everybody seeing that?
Now I
Yes? So the difference is H2O, which is nothing but water. So yes, if we have higher concentration of the alcohol, then the reaction goes in this direction. But if we have higher amounts of water, the reaction goes back. But it is also in presence of an acid. Acid is the catalyst in both cases. If you remember the mechanism we wrote, catalyst was used, catalyst was created all the single time. So the catalyst is the same. Catalyst is never a reactant, catalyst is never consumed. Catalyst is the same. The reactant for the forward direction is the alcohol with the ketone. For a reverse direction is water. Acetals can very easily be hydrolyzed back to the parent aldehyde or ketone and the alcohols or the diols, whatever they are. Does that make sense, everyone? And that is one of the reasons why they are so popular for organic chemists, and we talk about how to use them. But let's first look into the mechanisms of the reverse process. Again, it's the reverse process. So think about, how do I go from this acetal? What do we need?
Water.
Dilute acid. Exactly, water with acid. What would the outcome be? Can someone please tell me, what would this create?
One of the oxygens would get
What would it create? You're right, one of the oxygens, blah, blah, blah. In the end, what will it make?
Acetophenol.
Sorry?
Acetophenol.
Actually not acetophenol, because there's no benzene.
Oh, yeah,
Acetophenol is for
I do that
benzene.
every time.
But I think what you're trying to say, you're pretending that's a benzene.
I am. I always do that. Let's put that on the test.
But that's kind of what you're thinking, am I right?
Yep.
Is that what you were thinking also?
That-
Kunal? Everybody agrees?
Mm-hmm.
So one of the most important things here for us is, and we'll write the mechanism in a second, but please understand, recognize your carbons. This carbon is the same as that carbon. The acetal carbon, where the two oxygens are connected, was the original carbonyl carbon. Let's write a mechanism. Please tell me, what do you think will happen first? What would you want to do first? We are going reverse direction. Protonate what?
Protonate an oxygen.
Does it matter which?
No.
Okay. What next?
Good leader.
It becomes a good leaving. Exactly. Which bond should we break to kick that out? The orange
No.
or the green?
The green.
Why the green and not the orange?
Because it separates it from the carbon.
Okay, fine, that's one reason. Why, but why not the other? Why can't the other happen?
Because you're
Which carbocation will be more stable, to have a carbocation there or have a carbocation here?
Tertiary carbocation.
And also resonance stabilize. We keep on forgetting the resonance stabilization, guys. That's important.
Resonance.
Having a carbocation there is not good at all. Of course, in this case, that would be primary. But this one is very good because, yes, absolutely, it's tertiary, but it's also resonance stabilized. So which bond will break?
green.
No one. Agreed? What will it create? Carbocation, yes, and then 2 carbons and OH. Agreed? It's exactly opposite. What should be the next step? Anybody?
Second oxygen.
Say again? You're trying to protonate that, but there's already a positive charge. So what do you think we want to do? Sure, resonance you can show. That's more of our understanding, and it's a choice. You can show the resonance structure, blah, blah, blah.
Nucleophile.
Nucleophile has to come in. What's the nucleophile? Water. Please compare these steps to the mechanism we wrote to make the acetal. It's exactly opposite. What will that create? What does this need to do?
Oh.
It needs to
Lose a proton.
lose a proton. Good. If it lost a proton, okay, but since I was doing hydronium, I'm going to keep that intact. So water is going to come and take a proton, make hydronium. Agreed? Of course, there's hydronium also. Everybody okay? Next step. Next step. Now you're ready to protonate one of the other oxygens. Which oxygen should we protonate?
The one that has 2 others.
Exactly. because then that becomes a good leaving group. Once again, if you follow through with the mechanisms we wrote for making an acetal, this is exactly opposite that. What next?
The leaving group leaves.
And creates a, what does that create?
The diol plus an alcohol.
No,
No. Okay.
a cation, carbocation,
A
which is
carbocation.
resonance stabilized by the OH. A resonance stabilized carbocation. What is this guy going to do? Might help to look at its resonance structure.
It forms a double bond and donates the proton.
Exactly. This is nothing but a protonated ketone. Resonance structure, if you think about the resonance structure, that's a protonated ketone. What does it need to do to give a ketone?
Donate the proton.
Donate the proton. My point is, if you compare the mechanisms of making an acetal to hydrolyzing an acetal, they are exactly opposite each other. Everybody okay? Yes? Okay, here's another one. Please tell me mechanism you will write at home this time. Again, you got to practice on your own. You got to go through the steps and reason them out as you go through them. So that has to be dilute acid, not concentrated. So making an acetal, we need a concentrated acid, but hydrolyzing an acetal, we need a dilute acid because you want more water. Okay, please go ahead, tell me what will that create, and I would recommend everybody write these mechanisms over and over again to make sure you understand. Please just give me the products from those mechanisms. You guys can plan or practice at home.
But will we get keys?
You can do it.
Yeah. Yeah, we
It's
can
the
do it.
same thing.
Oh, yeah.
But if you write it and you want me to review it, I'm happy to.
Okay.
So, please give me the products. And there are more examples in the worksheets that I have on Canvas with keys and all. I think there's lots of examples. You lost a carbon. Which carbon is your acetal carbon? I did that first too in my head, and then I realized, no, wait, slow down.
But I just draw the same thing.
Hmm. Hmm. We can help our, we can give Camilla feedback and suggestions and hints.
Mm-hmm. Yeah. Since a cyclopentane ring would just.
No. 1, 2, 3, 4, 5, 6.
Oh.
Ooh, okay.
Wait, did I have too many now?
You're right about the 6th part, but I think we lost a carbon somewhere.
Did I?
1, 2, 3, 4. Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We added two extra carbons.
Oh, we added carbons, not take away. We added carbons. Thank you, Carter. And plus, look at the bonding patterns. Someone can help Camilla out. Also, by looking at the structure of the acetal, can you tell whether the acetal came from a ketone or an aldehyde? Which carbon is the acetal carbon?
This one.
Is there a hydrogen? Yes, exactly. That's what I did first too.
Okay.
Is there a hydrogen on this?
Yeah,
So, did it come from a ketone or an aldehyde?
an aldehyde.
Exactly. So that might also give you a hint that, oh wait, there's a hydrogen on the acetal carbon, so it came from an aldehyde. Are you all seeing that? Yeah. Yep. You got it. Exactly.
Okay. And then it would be like.
Exactly.
Like my carbons, right?
Exactly. No, yep, you did. Exactly.
Yay!
Exactly. So the
Woohoo!
point is, see, this is the acetal carbon, right?
1, 2,
Now notice, did this come from an aldehyde or a ketone?
Ketone.
Because there's no
Ketone.
hydrogen on it, right? So we are breaking this bond and we are breaking this bond and adding water. Where is the oxygen of the water going? Oxygen of the water is going here. And the hydrogens, one hydrogen is going here, one hydrogen is going there.
Oh.
Do you guys see that? Without writing the mechanism. So similarly, in this case, that's the carbon, that's your acetal carbon. Does it have a hydrogen? Yes, it has a hydrogen. So this came from an aldehyde. Agreed? And then we are breaking this bond. What are we putting on the oxygen?
Hydrogen.
Hydrogen. We are breaking this bond. What's going
Hydrogen.
on the oxygen?
A hydrogen.
And what goes on the carbon?
And a C and double bond O and
So
an
the
H.
oxygen of the water goes there. That's a shortcut way of figuring it out. Does that make sense? Can we do that for this guy? You can do it. Hey, if you want, nobody's challenging you, nobody's running over to knock you down and take your place. I would love it if someone were, but not knocking you down part, but running over to give it a shot.
So,
Looks like our product is an aldehyde. Our product is an aldehyde because it has an H on that carbon.
What I would do first, if you guys are thinking about the ring and all, is just make the changes, keep the shape the same. Just make the changes that need to be made,
yeah.
and then decide, okay, what does this mean? If
It can't be a ketone. It can't be a ketone.
I think I got it.
1, 2, 3, 4. 1, 2, 3, 4, 5.
did we lose a card?
This, oh,
Sure. Mark.
I think I got it.
Yes.
Yes?
Yes, absolutely. Yeah, so keep the shape the same, just make the changes, and then decide if you want to draw it again or not draw it again. That's totally fine. That's totally fine. That's absolutely right.
Let's see.
Ah, I think so, yeah, so,
1, 2, 3,
yeah,
4, 5.
I think so, yeah.
Sounds a bit right.
You guys agree?
Yeah.
Everybody agrees?
Yeah.
There you go. Please, write mechanisms. Make sure you understand how and why and all of that stuff. Because this is actually both making an acetal and hydrolyzing an acetal mechanisms are very common. So to be asked during exams. So please practice those. But what is the purpose of an acetal? And the main reason acetals are so popular for organic chemists is that acetals are a very good protecting group for aldehydes and ketones. Let me explain what that means. Okay? Let's say, excuse me. Let's say I want to do this reaction. Actually, that's wrong. That's not. Let's say I want to do this reaction. Can someone tell me what steps would I need to follow to convert this reactant into the product? Anybody?
Sorry, could you repeat the question?
How will I go from here to there? Reactions, schemes, process.
Eventually.
Lotus? What?
I'm saying, I feel like eventually you add Grignard.
So you're thinking Grignard,
Yes.
right? That's a strategy in our heads. Why are you thinking Grignard? Because we got into tertiary. So notice how this portion is right here,
Yep.
right? We brought this in.
Mm-hmm.
Agreed?
Mm-hmm.
So, good. So go along that. So then what should be step number 1? What would this have to come as? Will this have to come as a Grignard or the aldehyde ketone?
Aldehyde ketone.
But that's still there. We didn't react that.
Wait.
So what would this guy have to come as? Is everybody following this or am I losing you all?
I think we're lost.
Okay, we are lost. Okay, let's pause then.
Kind of lost on this one as well.
If you want to use Grignard chemistry, can you tell me, this is my target molecule, right? What would that, forget about this guy. It doesn't exist. How will I make this bond? What do I need to use and what Grignard?
One would be like a
Propol.
Are we going based off of Grignard being the first step?
That's for you to decide. Forget about this. Oh, okay, I'm erasing. Doesn't exist. I just want you to tell me everybody, and this is not, I'm not just looking at, it's for everyone. If I wanted to use Grignard chemistry and make this tertiary alcohol, what is my aldehyde ketone? What is my Grignard?
aldehyde ketone is like the ketone. The ketone would be
Acetone, how about that?
Yeah, acetone. That was what I was
Isn't
about
that
to say.
right?
Yep.
This will, sorry. Oh, I'm wearing a band-aid. I have a handy eraser now.
Oh.
Yeah, and I'll have to go and change.
Maybe
I just realized what you're doing. This is the aldehyde or a ketone, isn't that right?
Yep.
Where is that coming from?
And
The acid.
And-
Isn't that right? We wrote this mechanism, right? We've written it thousands of times. So, what is the Grignard? This portion is coming in as the Grignard. Isn't that right?
Yep.
Everybody good? Do I have you back? Everyone?
Not me.
Will this be the Grignard?
Yes.
Possible.
Agreed?
Yep.
Everybody okay now? My question is.
Oh yeah.
My question is, So basically what I'm saying is, okay, so if I'm starting with this compound, how do I convert it into that? So how do I first make that into a Grignard? Come on guys.
React it with
Numbers.
magnesium.
Okay. Once you've made it into a Grignard, now you will react it with acetone and blah blah blah. Does that look reasonable?
Yes.
There's a very big problem in that synthesis.
Mm.
Can you tell me what the problem is which will cause this reaction to not work the way we are planning to make it work?
The second step.
Second step is perfectly okay. Okay, how about I give you the hint? Second and third are not the problem. Which means first is the problem. Out
Magnesium.
of 3, 2 are not.
Ha!
Magnesium.
Why
First
magnesium?
step is a huge problem. Why? That's a great question. But that's
Magnesium.
my question.
Magnesium oxide.
Why is this step such a big problem? Can I?
The Grignard's gonna attack itself.
We cannot make a Grignard in 2 cases. What are the 2 cases where we cannot have Grignards? One is if there's a proton around, right? You can't make Grignards if there's an alcohol or carboxylic acid or anything because Grignard is a strong base.
What about oxygen?
But we can also not make it a Grignard if there's an electrophile. Because Amaya, I do know, I just can't get the word as out of me. As Amaya said, is once you get Grignard, if you made it BRCL, who cares? Wouldn't it just react with itself? It has a reaction site right there. So that's a huge problem. But what if this step is really essential for my synthesis? Whatever it is that I'm trying to do in the lab, I have to do this. So that's where we end up using acetals as a protecting group for aldehydes and ketones. So this is instead what I will do in the lab. I will start with this, but then first protect my ketone. Protect it. How do I protect it? By making an acetal. And of course, cyclic acetals are better than acyclic ones. Protected it. Acetals do not react with base, not at all. They're totally safe with bases. Oxidizing agents, acetals do nothing. Reducing agents, acetals do nothing. The only thing they react with, as we saw, react only with what? What's missing here?
React only with
As we saw, we wrote
Hydro-
mechanisms.
hydronium.
That's the only thing they react with.
Oh.
So, we convert the aldehyde ketone into an acetal. Then we make a Grignard. Is this an acid? Mg. Is it acid? Is it H plus?
No.
No.
No. Acetal is totally safe. Doesn't do anything. We can make a Grignard.
Mm.
Once we get a Grignard, we react it with acetone or whatever the aldehyde ketone was. Is there an acid in this system right now?
No.
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 Acetal is safe. Doesn't do anything. Grignard does what it needs to do. Is reacts, this reacts here, blah, blah, blah. So, acetal remains intact, doesn't do anything. O minus. Agreed? Now, what's our next step after that? What do we have to do to get rid of O minus?
Protonate.
Protonated using
An acid.
hydronium acid. That's when acetals are not safe. But what happens to acetal with hydronium? What does it become? It goes back to what it was. And what happens to O minus?
It gets protonated.
Did I just lose? Yeah. So we use acetals in very creative ways to achieve reactions which otherwise would be a problem. For whatever reason there might be, acetals can be used to protect the aldehyde or ketone, and then you can deprotect it. Does that make sense, everybody?
Mm-hmm.
Yes? Okay, so here's another question in that regard. By the way, who reacts faster to electrophiles? Is it the aldehyde or the ketone? Aldehyde. So, if we had, let's say, for example, and I want to convert can I do this? How would I do this? What would I use to reduce a ketone to an alcohol? Anybody? That's an oxidizer, not a reducer. That actually takes you in the opposite direction.
Dial.
No. Oh, are you giving me the actual synthesis, Carter? Or are you telling me what is needed to reduce a ketone to an alcohol?
What is the needed reagents?
For ketones to alcohols? No.
Oh.
It's a reduction reaction. Law? Law, you can, sure. Or what's the weaker version of La?
Sodium
Sodium
borohydride.
borohydride, right? So the point is we can either use La or sodium borohydride, but the problem is what? What's the problem? It will react with both. Not just one or the other, it will go to both. This
Excess.
will not be the product. The product will end up being the primary alcohol here and secondary alcohol there, but that's not what I want. Make sense, everybody?
Mm-hmm.
So, what's the solution? So this won't work. What's the solution? We are going to use an acetal to protect what? What are we going to protect?
The aldehyde?
Why will aldehyde be protected but not the ketone?
Because it reacts fast.
Exactly. Aldehyde reacts faster than ketones. So in preference to ketones, aldehydes will become the acetal while the ketone, for most part, of course, will I not get any ketone? No, I'm not saying that, but that will be the major product. Absolutely. Now that's protected. What do we do next? We can now bring in the reducing agent. There's no acid there. If the reducing agent comes in, it's generally used with methanol or ethanol as the protic solvent. Which functional group changes?
The ketone?
Becomes a what?
An alcohol.
What happens to acetal? Nothing.
Nothing. Yeah.
Stays the same. Now what remains to be done? We need to get rid of this. So we can get the aldehyde back. How do I get rid of the acetal and get the aldehyde back?
React it with hydronium.
So again, what's the purpose of the acetal? It's to protect this, then you do what you need to do every other places and then come back and deprotect it. Make sense, everybody? Okay, I know I'm almost out of time. I still have a couple of minutes. I need you on Monday, I need you to tell me the following. And I need you to tell me, okay? So I'm going to write a few syntheses. The question for you is, tell me how. What are the reagents you're going to use? What is the sequence of events and blah, blah, blah. Excuse me. What are you doing here, Sandra? That's not allowed. the others we've already done. So I'm like, we've already done this. And one is absolutely wrong. I wrote it though, so I can't blame it on anybody else. What are you doing there? Okay, well, let's just do that for now.
You could send us on,
So, yeah,
email us.
this is okay.
Okay.
Just
Yeah.
tell me how, please. Okay, so we'll stop right here. So the quiz on, not quiz, there's no quiz. Exam on Monday will cover
Tuesday.
through here.
Tuesday?
Tuesday, did I say Monday? Okay, well, you know what I mean. Yes, Tuesday, you're absolutely right. Oh, we don't have a room yet, right?
Yeah.
Okay, so,
Somebody's got a picture.
oh, give me just a second, my brain. Most likely, we'll be in 105 over there.
105.
Is that room okay?
Yeah.
Everybody is okay with that? So most likely we'll be there for the exam. Yes.
I actually like that room.
I don't
Oh,
like that.
yeah, the lab.
I like this one.
Guys, can I please have your suggestions? When are you going to give me your lab notebooks for the lab you finished yesterday? I don't really care. The less grading I have to do, the less headache I go home with. Yesterday I had a bad
Grade the
headache.
exams over that week and then you
Yeah.
have to grade anything until the last.
We're trying to make it easy for you.
So, so
You're welcome.
thankful. I am grateful. But if anybody does finish it and wants to just bring it next Tuesday, that's fine. Just bring it. So it's okay. Either way is okay. What? Oh, is that right?
He moved them.
Ricky.
Oh, at least, because I moved mine to Tuesday. No, it used to be that we'll both have Monday exams every single time. Are all our exams
Both?
So I moved mine to Tuesdays now. So at least there's yeah, it was not that we didn't plan it that way.
Uh-huh.
I think it just coincided every quarter, every single quarter. Ochem bio together. Ochem bio together.
Wow.
Even
Final exam note. I think that would be different. But
Oh
yeah,
my
as far
God,
as
that would have been
and we never
heavy.
consulted or decided none of that. It was